It's just me and the professor by ourselves. No one else is here. It's really strange.
Especially the ones who might end up taking 3 calc and say in the next way possible, taking 12 then.
I wouldn't mind if it wasn't that I need to be focused, so it's kind of hard on me. So I wanted to talk about normality because a few of you rightly so asked what's the big deal with normal subgroups. And normal is one of these words that we use across math and abuse completely because we have normality that you just learned from linear algebra. We have normal functions. So we have all kinds of normals all over the place. But this normal, I think that Fraley does a very good job explaining. So I thought I'd really go over what he does in the book and then connect it to what you've been doing in class. By popular demand, I listed which slides have the homework. So you can actually go back and look at the first slide and find the slide where the homework is listed. Just to remind you, the exam 2 is next week. I'll have computational problems and true-false. You've had some computational problems to give you an idea. I do imagine that when you're doing the homework that I've assigned, that one of the first steps is to play around with some examples. I can kind of see from your homework that you're doing that. Plus, I also, not on purpose, have asked you to do some computations, and then some of you have linked that to the homework and said, oh, the quaternion group can be used here as an example. So I think that we're doing that anyways, but just to give you a heads up, there'll be some problems where you just are asked to compute some things. The one thing I'm a little bit nervous about is on the presentations. So on the homework problem, some of you went straight to the matrix representation and then used that to come up with the Cayley table. And the idea, what they wanted you to get from that is that the presentation is all you need to actually develop the Cayley table. So as I did the homework the other week, I showed you can actually, that's all the information you need, that those restrictions and the fact that these are the generators of the group, those two things combined create the Cayley table. So I was thinking of asking a question like that on the exam where you wouldn't get a matrix representation. So you would have to understand that this representation or the examples that you have in the restriction is what gives you the Cayley table. So if you did it using the matrices, go and review the homework solutions that I posted or the videos I posted on the homework solution. So you're very clear that the presentation is what gives you the Cayley table. There'll be true and false questions. I think every math professor loves those, right? We all love them. So they're on there. And one proof that will be from the homework, and one proof you really haven't seen before because I've not really been following the homework in the book. So, so you really wouldn't have seen anything. It won't be directly from the book or something. It's probably something that'll fit. And next week, I was scheduled to be gone on Wednesday. Recall that our tests were supposed to be on Mondays. I actually am the opposite of most professors. I don't like the test being given when I'm not here, just because I'm not here to answer questions, or if somebody has something they want to see me, you know, you've come to my office before class. I kind of like to be around a little bit. Are you guys okay with having the test Monday and not Wednesday? We'd have to have it in this room, but we can make the room more airy by taking this desk and moving it aside and spreading the room out a little bit.
We couldn't push it back to the following?
We could, but that makes it really cramped for you for the third test. Not enough time between the second test. Yeah, you're fine to do that. I'm okay with that if you want to do that.
Third one?
I don't know, but I spread them evenly apart. Well, so that will automatically push it so that they're closer to each other. April 20th is the third one. So this would push, there would be 2 tests in April. I don't know if I like that.
We have quiz on Wednesday.
Yep.
Right?
Yeah, but knowing that we have the exam, I'm looking at the quiz. You only had really one real homework problem on this set. Most of them were computational. There was only one real interesting. Is that another way to say it? Interesting problem. And so I've already developed the quiz for this one, and I think it's something very doable from looking at your homework that I just graded. And also your responses when you talk to me over spring break. Do you guys want to think about it and me do a survey monkey and do a vote? Whether you want to push it back one more week to the following Monday, or you want to, let's do it that way. I'll do survey monkey so it's anonymous. To your vote the way you want to. So either we have it that Monday or we could do it the following Wednesday. I prefer the Wednesday because of the room.
So we're talking March 23rd or April 1st?
Well, let me see. Yeah, April 1st. So I'll send out just, preference of either day, and you guys can choose a day. So we are now covering sections 13 and 14. They're related. I don't know how far I got on homomorphisms in this lecture because I wrote the lecture a little earlier. But the homomorphisms and the normality of the groups are very connected to each other. And I took a picture from the top I try to make the PowerPoint relevant to whatever we're doing. This is an image of what you should be thinking about. So for example, in Z, when you go to Zn, you're really taking the big set Z and then making it into these small, manageable packets. That's what you're doing when you're looking at cosets and you're looking at normal subgroups. You're modding by the normal subgroup, and you're starting out with your big group and making it into more manageable packets. So I want to give credit. There's really nice stuff out there that wasn't there, I think, the last time I even taught abstract algebra. In fact, I know that it wasn't there the last time I taught abstract algebra because we got a lot of hits on our own videos that we were making, and we weren't making videos every day. So that means that there's really nothing else out there. But there's a guy, Math Dr. Bob. I don't know if anybody's seen him on YouTube. Oh my God, he's so patient. I read this and I watch him give his lecture, I think, wow, he's incredible. So he actually gives more detail than I am giving here. I'm kind of integrating it into what we're doing in class where he's really slowly going through every little piece. So I really recommend his site. So in Fraley, they present sections 13 and 14 in a linear fashion. And I think that's something Fraley does, which I don't really like, where he goes through like a little staircase when they're interconnected ideas. So I just want to warn you, if you're reading through Fraley, you might get that feeling that there's separate, disconnected things, but they're actually related to each other. So let's start, instead of the Fraley approach, with a bird's eye view of what this is all about. So start with cosets. Recall that cosets are formed by taking a subgroup. So you start out with a subgroup of the big group G, and for a fixed element A and G, you write its coset down, AH. And this is the definition. The left coset looks like this, and we know that the left coset's partition G. So basically, you can take G and chop it up into pieces based off of its left cosets. The advanced crew in this class can start thinking about whether which theorems hold for infinite groups and which theorems don't, and how can you extend them, if at all. So for example, Lagrange's theorem can't be extended for, or doesn't work for an infinite group because it doesn't make sense. But can you write down any theorem that talks about cosets of an infinite group? I'm sorry, that was a half-baked idea on my part, but I was thinking, I want to think about this. Well, maybe I'll give it to you guys to think about. I'll keep you from doing your Forgaston work. So recall what a partition means. This is the math symbol of writing a partition. The one is that all of them have to union up. It's this picture, right? You have to be able to union up all the cosets and make G. And I indexed it purposely here as A and G, so I didn't say that it has to be finite, just to get that idea starting. I don't know the answer to that one, by the way, what you can extend and what you can't. And if you have two cosets and they're not empty, they're going to be the same coset. There's no way that you're going to get some cosets overlapping a portion of the other one. So let's start with an illustrative example. S3 is a symmetric group of permutations with 3 elements. It's the same thing as D3 if you want to think about it geometrically. So here's an H. We can take H equals 2, 1, 3. 1, 2, 3 goes to 2, 1, 3. Or you can write it in terms of a transposition. 1 goes to 2, 2 goes to 1, and 3 goes to 3. And it's a subgroup. If you just want to verify it, E is in there. and 1, 2 squared is E. So it's definitely closed, and the inverse of 1, 2 is itself. So it satisfies the 3 properties of the checklist conditions of being a subgroup. So that little thing I made is actually a subgroup. And I can list out the cosets. I have H, 1, 3H, and 2, 3H. Those are the different cosets. And I went through the calculations here for you so you can see it actually mapped out. And I think I grabbed this example from Dr. Bob, Dr. Math Bob, or whatever he calls himself. And I don't think he went through that detail, but this is the kind of detail I went through. But on all other counts, really good. Please do the computations if you're not familiar with working with permutation groups. So go through these, and actually that's how you can practice and integrate it with whatever we're doing here, so that you 2 birds with 1 stone. So I just wanted to show you what I meant by computation. So if I take 1, 3H, that's 1, 3 slapped onto each element in H. And what do I fill in there? I get 3, 1, 2 when I do the composition. I literally do the composition with each element, and this is the end result that I get. And I just checked. The union of all these left cosets indeed do make up G. It's incredible, but they do. Because that's G right there. That's all of the permutations of 3 elements. And they turn out, if I write it in transposition form, it turns out to be exactly these elements, which turns out to be all these guys up here. So I've got everything covered. You know, when you're writing this down, you don't think you have it all. It's not possible, but it actually does turn out to be everything. So I only did this for one of them, one of the examples that I'm doing, but just to give you an idea of how to do it on your own, I would try it for the other example that I'm going to cover, where I don't fill in the details. So if you're not as familiar with permutation groups, try it out. So they're all in there.
I'm sorry, can you go back to where you did 1, 3 on the left of each element in H? Why do you compose 1, 3 with 2, 3?
Did I make a mistake?
Because H is E and 1, 2, right?
Yeah, it should be 1, 2.
Okay.
Hopefully I meant to write 1, 2.
Okay.
It must be, because otherwise I wouldn't get the whole thing. This is with sleep. I have no excuse. I don't know what to say. Okay, I'm going to do a second example, but I'm not going to do all the computations through. Left cosets of H and 1, 2 are going to be, I'm just going to give you the answer. So you can fill in the details like I filled in the details for the first example, so that I wrote those out so you could see how to do it if you're not as comfortable with it. So here is the subgroup H equals E1, 2, and here is the subgroup H equals E1, 2, 3, 1, 3, 2. This is a subgroup, just like the first example. These are the cosets, just like the first example. I just left out the computations this time. What do you notice about the left and right cosets? These are the left cosets of this subgroup over here. These are the right cosets of this subgroup over here. These are the left cosets of this subgroup, and these are the right cosets of this subgroup. Take a look at it and see if you can figure out what's different about these two subgroups.
They're gonna change,
If you look at that one over there, do you see it, Paul? This one's messed up. You see it? It's the left cosets all unionize out to be G, and the right cosets all unionize to be G, but they're somehow like mixed up, right? The left coset, like this 1, 2, 3 is covered in this coset over here, and that 2, 3 is covered over here, and this is not like even that you can match up a left coset. There's no pairwise combination of the left cosets with the right cosets. They have nothing to, it looks like they have nothing to do with each other. There's no algorithm to come up with the right cosets from the left cosets for this guy. Whereas this guy, they're matched, right? They're all matched up. The left cosets do equal the right cosets. So in some way, this set right here is really nice because I can predict what's going to happen for the right cosets once I have the left cosets. This one's messed up. This one's normal, this one's not. And that's the difference between mapping out what's normal and what's not normal. You can't identify the right cosets from the left cosets. Why is that a big deal? So what? Big deal. And it's not even that, you know, maybe one of the cosets is going to be coming up somewhere else. They're really random all over the place. Everything's covered. It's just not nice. So what's the real definition of normal? In Fraley, they talk about this definition. This is the symbol that we use for normal. It's this triangle that points this way. N is a normal subgroup if the left cosets equal the right cosets. Well, that's not a nice definition if you have to prove something. If you have to prove something is normal, then the only way to use that definition is to actually list out all the left cosets and list out all the right cosets and show they don't equal, which is a big pain in the butt. So you don't want to do that. So that's a difficult thing to check. And an equivalent, more readily checkable version of this, this definition is to, I used H here, great. But if you have an H that's normal, it's got to satisfy this property. This is a very checkable condition. And so that's why we use this condition versus this condition. But the meaning of normal is probably more, a bird's eye view is better, this one is better than that one to understand what's going on.
Left-pointing triangle?
Yeah, it's a left pointing triangle. You've seen it before? I'm sure. Well, that's, I think Fraley uses this. Yes? Yeah. It's standard. It's standard notation. This triangle was already used. That triangle was already used. So you point at this triangle. We didn't use that triangle yet. And I just wanted to show you this. If you take an arbitrary H and take an A that's in G and actually check, I'm just checking the left side here, it actually fails that checkable condition. So I'm checking whether I can take a random element from the big group G, which is S3, and then take, that's my A, so I took A to be 1, 1, 3, and then I took H to be any element in the group, which in this case, I have H equals 1, 2, which is the only interesting element in this subgroup. And I calculated A inverse, and what I get is 2, 3, which is not in H. So it fails the checkability condition. So I can prove that this left example is not a normal subgroup. On the other hand, I'm just going to take one element here and do the same calculation, and I randomly took it out of my Swiss cheese brain, and I get an element here, 1, 3, 2, which is right here. Right? It's in the group, in the subgroup. That's not a proof, because I just did one. But you could actually check it one by one for every element in G. So it's not that bad because you're working in S3, which is not that big. Clear so far? Why did I choose S3 to do all my examples? I don't have to ask you this because I think everybody's doing this in class. S3 is not abelian. That's number one. So when I create an example like this, I have to think, I don't want to go too big, because if I go too big, I'm going to give myself a headache. And I have enough a headache. Right? You already heard my little girl. So I have enough going on there. So I want to choose something small. But I don't want to choose something abelian. Why don't I want to choose something abelian as my example to start thinking about what is normal versus what is not normal? It's automatically normal, right? Left cosets will equal right cosets if it's abelian by the definition in Fraley. So I have to choose something not abelian. So I chose the smallest thing I could think of that's not abelian. And so that's why I chose S3. Why is this important? Well, you just came up with abelian groups contain only normal subgroups. So I'm not going to get anything interesting there. What if I want to create a subgroup? Is it possible to have a normal subgroup inside a non-abelian group? Well, the center is always a normal subgroup. And so if I wanted to, I mean, you can kind of think of, well, if I can make a cyclic subgroup that's proper inside the big group, that will be normal because it's going to be abelian. So you could make one like that. But you could also go to the center. The center is always going to be in a normal subgroup. So I have one for free. So this is just if you want to make up some more examples yourself, or if you have a exam question you come across where you wanted to true-false something with an example and you need to come up with a normal subgroup. Here's one. Let's say, true-false. All non-abelian groups have non-normal subgroups, for example. False. I'll give you a counterexample. Look at the center. Well, so what? So now we can compute them. You know what it is. You know the definition. What's the big deal? Why do I need them? What's the big hoopla over normal subgroups? Well, on page 98 in Fraley, 98 and 99 have the best two images in the entire book. So on page 98 of Fraley, he has a subgroup. This is Z6, bless you, under addition. And he's put the Z6 in such a way so that he's color-coded it in shades of gray in your book. But I have color at my fingertips here. So I called the little subgroup the little group 03, I put them as green. And the 1-4, I put them as blue. And the 2-5, I put them as yellow. And what happens is that if I cross 03 with 03, I get 03s back. And if I do this addition over here, I get 1-4s back. So you see these patterns. I see huge blocks in there which have only the elements. The yellows are only contained in this block. The greens are only contained in this block. And the blues are only contained in this block. So there's some kind of self-containment going on. And in fact, if I just eliminate those numbers and just represent the G by the little rectangle 03, I just get rid of that rectangle 03, and I put G there to represent the rectangle 03, I have a group. I have a group of 3 elements. It works. Binary operations there, Cayley table's a Latin square. So from my big group, I've made a small group. And that's really cool. And that'll only work if your subgroup is normal. When these are not normal subgroups that you're working with, the normal subgroup that they're using as a generator, I believe, is 03 here. But if they're not normal subgroups, the colors are scattered. And they have a picture on page 98 where they try to do the same thing. So over here in this first 03 in Z6 is a normal subgroup. 0 plus 0, 0, 0 plus 3 is 3, 3 plus 3 is 0. So it's self-contained subgroup, it's a cyclic subgroup. So they did the same thing on page 99 with a not normal subgroup. They tried to do this. And instead of getting this nice little blocks set up, they got a big scattered mess. I think you're looking at it. If you don't have your book with you, look off of someone who did, because it's valuable to look at that picture. It's on page 99. You see the difference. There's no visible pattern when you try to do